Hello my scholars, you're welcome to my school YouTube channel. My name is Emmanuel, and in today's video we'll be looking at JAMB CBT past questions in chemistry for the year 2024. Don't go anywhere, stick around and we'll be right back. You're welcome back to my school YouTube channel. In today's video, we'll be tackling question 126 to 138. Now, let's get down to question 126. An example of a compound that is acidic in solution is. An example of a compound that is acidic in solution is H3PO4, NH4Cl, Na2CO3, MgCl2. When we are talking about a compound that is acidic, it means that all of these actually are salts, okay? But which one is acidic salt? You know, we have different types of salts. We have the acidic, we have basic, we have neutral, we have double salts, we have the complex salt. So don't forget that salts generally are compounds that are formed when metals replace, or metallic ion or ammonium ion replaces hydrogen ion that is present in the acid. So what compound that is formed is referred to as salt. So salts are compounds that are formed when a metallic ion replaces the hydrogen ion that is present in an acid, okay? Or ammonium ion replaces the hydrogen ion that is present in an acid. So if we are talking of a compound that is acidic in solution, it means that it is actually acidic. It could be an acidic salt, okay, when dissolved in water. Let's look at option A. Says H3PO4. Of course, this is an acid, okay? So if a metal is coming, a metal will replace this hydrogen, let's say sodium for instance, okay, or let's say we have potassium coming in here. It's going to replace this hydrogen, okay? We can have maybe part of it or all of it. Of course, it will not be all of the acid. You can still have just one that is what? That is left, okay? Like I have K2, for instance, HPO4. So that could be acidic. For this is ammonium chloride. This is also, this ammonium has replaced, you know, the hydrogen. Of course, this is Cl, so it should have been from HCl. So ammonium ion has replaced the whole hydrogen that is present here. So this cannot be acidic. So when a metallic ion or ammonium ion replaces all the hydrogen that is present in the acid, we said we have formed a neutral salt, okay, or a normal salt, okay. So ammonium has replaced the old hydrogen that we have from HCl to form ammonium chloride. So this is a normal salt, okay? This is not acidic in solution, okay? This one is sodium carbonate, okay? Carbonate, of course, should have been from H2CO3. H2CO3 is the acid, though it's a weak acid, okay? So we have sodium coming in, sodium ion replacing all the hydrogen that is present in there. So it should have been H2CO3, then most of sodium came in to replace the hydrogen. So this is Na2CO3. So this is also a normal salt or a neutral salt, because all the hydrogen ion that is present in H2CO3, which is the acid, has been replaced, okay? And then we don't have any. So this is also a normal salt. Then we have also here magnesium replacing, this is chloride, okay? Chlorine, it should be having HCl, also hydrogen chloride, okay? Or hydrochloric acid has been replaced. Magnesium has replaced the hydrogen there, so there's no hydrogen left here again. So all of this, so this is a normal salt, this is a normal salt, this is a normal salt, but this is acidic, okay? So this, an example of a compound that is acidic in solution because of the presence of the hydrogen ion that we have here, is H3PO4. So the correct answer is option A. Now question 127. The amount of water a substance chemically combined with is called water of what? If you have gone through, or you know what salts are, like we said earlier on, okay, we discovered that there are some salts that absorb water, okay, when they are exposed to atmosphere. There are some that absorb water when they are exposed to atmosphere and then they turn into solution. There are some that when you expose them to atmosphere, they absorb moisture or absorb water to become sticky when you touch them. And there are some kind of salt that when you expose them to the atmosphere, they lose their water of concentration, okay? Their water of crystallization or water content, the moisture content they have in them, they lose that water, and then their mass will reduce in that part. In this case now, the question says that the amount of water a substance chemically combined with. So when such salt is exposed to the atmosphere and then it absorbs moisture, okay, we say we have what we call water of crystallization, because you can still, it is moistened or it is in solution, you can still recover your salt back that has no water. All you just need to do is what? Apply it. When you apply it, you will get your crystals back, crystals of the salt. Okay, so that's why we refer to it as water of crystallization. So it is not dehydration. If it's dehydration, it would have been that water was removed. That means water is not present. If it is solution, that means we have had a solute dissolved in solvent for us to have a solution. But if that happens, it will not be that the salt still has some water content in it. So it is not option B. Option C says hydration. If it is hydration, we would have had some quantity of water in it, but not chemically combined to form this water with the salt. Okay, for option D says crystallization. If you have hydration present in it, if you eat it, you can't have the crystals of that salt back. Okay, but if it is water of crystallization, on eating, subjecting it to eating, what happens? You get the crystal of your salt back what it was. So salts can actually combine with moisture, okay, and then we call that water of what? Crystallization. So the amount of water a substance chemically combined with is called water of crystallization. For instance, let's look at the board. We can have situations where we have Na2CO3, okay, and then we have dots, okay. We can have X moles of water. Okay, so this is what we call the water of crystallization. The number of moles, we can have 10 of it. Okay, so 10 moles of water. We can have also commonly, like we talk about in rusting. Okay, rust has this, okay, H2O. Of course, this is hydrated. This is what we call hydrated iron 3. Yeah, that's 6, that's 2. Yes, iron 3, hydrated iron 3 oxide. This is what this is. This is hydrated. So if you apply, because this is what loosely bounded to this. In this case, if you have this solution is going to turn, once you expose this, it's going to absorb moisture and then it sticks to this, okay? And then, but if you apply it to this, you can get this back. This water of crystallization can be lost, of course. If you lose 9 moles of this, okay, we can have just NaCl. Let me say this, we have Na2CO3. If you apply it to it, then we have dot H2O. Okay, you'd have lost about 9 moles of water, would have been lost from that. Okay, so this, but in this case now, this is iron oxide. Okay, if you apply it to this, just like your rusting has taken place, H2O remains. What will just be done is that what this one is stuck to this. So this is hydrated, because I'm trying to differentiate between dehydration and then the crystallization. So, but in this case now, you still get this. You cannot get, this is a chemical reaction, okay? You cannot get this back because rusting has taken place. The iron, no matter what, you cannot apply it to this and then you get this iron back. And the oxide, you can't get it back. You have formed a new substance. But in this case now, this is chemically bounded to this. Because it's chemically bounded, if you apply it to this, the water of crystallization can be lost and you can still get the crystals of this salt, Na2CO3. So for that reason, let's move back to the screen. The amount of water a substance chemically combined with is called water of crystallization. The correct answer is option D. Question 1 to 8. Heat of solution involves 2 steps that is accompanied by heat change. The energies involved in these steps are what? Now, when we talk about heat of solution, 2 things are involved. There's going to be a breaking of bond, okay, of the ionic solids. Okay, don't forget, before we talk about solution, we talk about solvent plus solute to give us solution. Okay, so the solutes usually are in solid form. Okay, so that solid, the ionic solid, now there's a bond that is holding the solid together. Don't forget, in ionic solids, we have the electrostatic bonds, okay, or electrovalent, yes, electrovalent bonds or electrostatic bond. Force of attraction between the metals and non-metals are so strong, okay. So to break that bond, there is going to be a breaking of bond before there can be dissolution of that solid in a solvent. Okay, so the bond that is broken, or the energy that is needed to break the ionic bond into, or to convert it into a gaseous one, is what we call the lattice energy. Okay, so for that solid to be broken down, there is need for energy. Of course, energy is needed to break down that ionic bond or to convert it into the gaseous ion. Okay, that will be needed. That is one. On the other hand, don't forget also that solid we need to dissolve. Now, there is an amount of energy that is required or that is given off whenever the ions are released from the lattice. Okay, we have the ions that are present because the ions need to be dissolved in the solvent. So there is an energy also that is given off when the ions from the lattice will be released so that it can dissolve in the water solution or the solvent, as the case may be. Okay, so we have two steps now and two energies. Now we talk about the lattice energy, which is the energy that is required for the ionic solid, okay, the bond to be broken down into the gaseous ion. Then secondly, there is also the requirement of the amount of heat that will be given off when the ion that is from the energy that is given off when the ion from the lattice, okay, is actually dissolved in water. Okay, so two energy, and that is what we call the hydration energy. So what we are saying in essence is, let's look at the board. For us to have heat of solution, two things are required. We talk about the lattice energy, and then we talk about the hydration energy. Hydration energy is the energy that is actually required for the ion in the lattice to be released so that it can get dissolved in water. So in other words, heat of solution is derived from lattice energy plus hydration energy. In some other cases, that means we can also have this moving to this side, so we can also say that hydration or lattice energy is equal to heat of solution minus, because you can move this to the other side, minus hydration energy. Okay, as the case may be. In other words, you can be also asked that what is hydration energy? Hydration energy is the subtraction of what? Lattice energy for what? From heat of solution. In other words, heat of solution is involving lattice energy and hydration energy. Let's move on to the screen now. So the question says heat of solution involves two steps that is accompanied by heat change. The energies involved in these steps are: option A says lattice energy and hydration energy. Option B says lattice energy and ionic energy. Option D says heat energy and lattice energy. And option D says hydration energy and heat energy. Heat energy is not what we require because we need to break the bonds of the solid, okay, and that is required by what? Lattice energy. Lattice energy is what is responsible. And then there's also the kind of energy that's given off when the ions that are gotten from the lattice, okay, begin to what? Dissolve in water. That is what we call the hydration energy also. So those two energies. So because of that, option A is the correct answer. Question 1 to 9. Question 1 to 9. We have a compound here. Okay, you can see it here. It says the IUPAC name of the compound above is. The IUPAC name of the compound is, we have a trival name, the old names that some of those compounds are called. Trival name, easier names that are easily called olden days. But the IUPAC name, a set of scientists, of course, chemists, they came together and then they decided that there should be a general name by which every compound are called. Okay, that's why we call them international, the IUPAC, International Union of Pure and Applied Chemists. Okay, so they came together and then they gave names to compounds, especially organic compounds. So those names now by which they are called is what we want to, the question is asking us to call this. Okay, so we want to give this name. Let's look at the board so that we can see what happened. It has been withdrawn here. So first of all, there's what we call the parent name. Okay, we want to find out what is the parent name. The parent name is the longest chain of carbon. Okay, and we have the alkane, we have the alkene, we have the alkyne. There's no double bond here, there's no triple bond here, so this is just what? Alkane family. So first we look at the longest carbon chain. Longest chain to form our parent name with, let's start, this is carbon 1, 2, 3. That is one route. 3 chains. Let's look at another one. Carbon 1, carbon 2, carbon 3, carbon 4. Okay. Then if you take it from here again, carbon 1, carbon 2, carbon 3, carbon 4. So which means the longest chain is actually 4. Okay. So we can take it, let's take it straight up this way. And we can take it from the back to carbon 1, carbon 2, carbon 3, carbon 4, whichever way. But ensure that the numbering, first of all, the numbering, we have 1, 2, 3, 4. Okay. Then 1, 2, 3, 4, whichever way. So the carbon atom of the alkane, because it's a carbon to carbon single bond, must be what? Butane. Okay, because butane has, if it is 2 carbon atom, if it is 1 carbon atom, we call it methane. 2 carbon atom, we call it ethane. 3 carbon atom, we call it propane. 4 carbon atom, single bond, carbon carbon, we call it butane. 5 carbon atom, we call it pentane. 6 we call it hexane. 7 we call it heptane. 8 we call it octane. 9 we call it nonane, and 10 we call it decane, as the case may be. So for this now we have about 4 carbon 1, 2, 3, 4. So that is butane. So we call that, you start with the parent name, the longest name first. That is butane. Okay, that is butane. So the next thing is to look for the substituents. Okay, the substituents are other functional groups that are not the major one, that are not the longest carbon chain. Of course, they could be halogens, like in this case where we have bromine, the group 7 elements. We could have the alkyl, okay, like this case now, this is a functional group because we are not counting, this is not part of the what? Of the straight chain that we're looking at, okay? So we have carbon 1, carbon 2, carbon 3, carbon 4. So on carbon 2, of course, we could also decide to name number from here, carbon 1, carbon 2, carbon 3, okay, and carbon 4. But if you take it from this point, we have 1, 2, 3. On carbon 3, that's where we have the functional groups, okay, that is substituent, this and this. These are the 2 functional groups that are attached to this carbon, okay. If we take from here, carbon 1, carbon 2, carbon 3, this will be carbon 3. So which means on carbon 3, that's where we have the 2 functions. But if you count from here, carbon 1, carbon 2, so this means that these 2 of them will be on carbon 2. And the rule says that go with the side that has the shorter route, okay, shorter, longer of this. So this one now, carbon 1, 2, 3. This is 3 coming from here. 2 of them are on carbon 3. But if you count from your left, 1, 2, carbon 2. So 2 is shorter than 3 from here. So we go with carbon. So this is carbon 1, carbon 2. Now we have 2 substituents placed or attached to carbon 2. Which is bromine, okay, and then this is what? This is methyl, okay, methyl and bromine. So which one comes first now? What the rule says, one of the rules governing nomenclature of hydrocarbon says that what? That whenever you have 2 different substituents attached to a carbon atom, you will take them alphabetically, okay, in order which comes first alphabetically, okay. Now this is bromine, that is capital, that is letter B, and this is methyl, that is M. Of course, alphabetically B comes before what? Before M. So that is bromine. So that means bromine, and this bromine, of course, we call it, there is a name, we have the suffix and the prefix. If it is coming before, it is called bromo, okay. So we call bromine because it is attached and it is a substituent, a functional group that is added. We call it bromo, okay. Then where we have this, the CH3, we call it methyl or methyl, okay. So we are going first with the bromo, and it is on carbon what? Carbon 2. So we will say 2 dash bromo, comma, we have another one here which is methyl on what carbon atom? Still on carbon 2. So that will also be 2 methyl butane. So that's the name of that. So the name of this compound is 2-bromo 2-methyl butane, or 2-bromo 2-methyl butane. So let's move on to the screen and let's see what we have. The IUPAC name of the compound is, option A says 3-methyl-3-bromobutane. So if it is 3-methyl-3-bromobutane, that means it was counted from this point, 1, 2, 3. Okay, 3-methyl and then 3-bromo. This is wrong because 1, bromo should actually come before methyl because alphabetically B comes before M. Okay, so it should have been. And secondly, it's supposed to be on carbon 2. You don't count from here because this is 1, 2, 3. You are supposed to come from this 1, 2 because this is shorter. So the rule says go with the shorter route compared to what? The third one. So that is 2. So this is 3-methyl. So this is not correct. Option A is not correct. Option B says 2-methyl-2-bromobutane. So counting from here 1 to 2-methyl-2-bromo. This is not also correct because we see alphabetically M is coming before B instead of B the other way around. So this also is wrong. Option C says 2-bromo, 2-methyl-butane. 2-bromo, 2 on carbon 2 bromo, then 2-methyl-butane. Yes, this is correct. Option D says 3-bromo, 3. It is not 3, it has to be 2. So the correct answer here is option C. Do you know you can take practice questions on our simulated JAMB CBT past questions? All you need to do is to click on the link in the description below that takes you to the Myschool website. There, you'll be able to download the Myschool mobile app for your Androids and Myschool software on your laptops and computers. Please go ahead and start practicing. Now let's move on to question 130, question 130. The shape of ammonia molecule is what? The shape of ammonia molecule is what? We have the V-shaped or bent, we have tetrahedral, we have coplanar, we have the trigonal or what we call trigonal pyramidal. Okay. Now there's what we call VSEPR. We have dealt so much on the shape of molecules, okay, in one of our video lessons in chemistry. So please just subscribe to our video lessons in chemistry so that you can have a good knowledge of this, okay. What we call VSEPR, that means valence shell electron repulsion, pair, okay, repulsion. There is repulsion usually. There are 3 things that determines the shape of a molecule. Number 1, we look at the lone pair of electrons that we have on the atom, that is what we call central atom, that is combining the other molecules. There's a central atom usually that other atoms of elements are attached to. How many lone pair of electrons do they have? Okay. Then secondly, we look at the repulsion between the electron. We call it repulsion between the electron, okay, pair of electrons. So number 1, we are talking about ammonia. Don't forget that ammonia has the formula NH3, okay, NH3. Now, the NH3 that we have there shows that nitrogen is actually the central atom. Let's look at the board so that I can explain further. We have ammonia is NH3, okay, that's the ammonia gas. We can draw it this way. We have hydrogen, one hydrogen here attached to it. So now nitrogen is the central atom, and we know that nitrogen has that 7, so that means it has 2 electrons in the first shell and then 5 electrons in the outermost shell. Now these 5 electrons that this nitrogen has, 3 of it would have been used in bonding with this man here, hydrogen, another one hydrogen, another one hydrogen. So about 3 of them, of the 5 electrons that is a valence electron that it has been used. So we have 2 lone pair of electrons that is left. So we have 2 electrons, 2 lone pair of electrons that is left. Now this lone pair of electron is going to cause a repulsion now between the bonding electrons. These bonding electrons that are bonded, it will be causing them to repulse, and then to repulse between themselves. Don't forget, we talked about VSEPR, okay, valence shell electron pair repulsion. There is always a repulsion between the electrons that are attached to what? To the central atom. Okay. Now in this case, now nitrogen has 2 lone pair of electrons that is left. Okay. So that will now be causing the repulsion between the atom of the electrons, the bonding electrons that are what? That are attached to this. So as they are moving apart like that, it bends of that. So we have about 3 of them. Of course, you can see this shape. We have this shape. We have this shape. Okay, maybe I didn't draw it well. Let's say we have it this way. We have it this way. Okay, so we have it. So this is looking like a pyramid. Okay, pyramid is what is looking tree. That's why we call it trigonal. Okay, this is giving us a trigonal, or what we call, is that we call it trigonal pyramid. Okay, of course it's looking like a pyramid, or we call it distorted. Okay, distorted tetrahedral. Okay, take note, distorted is distorted. It's not like the normal tetrahedral, that shape that we have. Okay, so we just go with trigonal pyramidal. Okay, trigonal pyramid. So it has a tree like a triangle. Okay, kind of. So because of the repulsion of the lone pair of electrons 2 that is left from this nitrogen atom, now it causes repulsion between the atoms. Let's move on to the screen and see what we have. The shape of ammonia molecule is V-shaped or bent. It is not bent. Okay, tetrahedral, it is not. If it were distorted tetrahedral, we could have gone for this. Okay, distorted tetrahedral is looking like a pyramid, like a trigonal pyramid. Okay, so it is not option B. Option C say coplanar. It is not coplanar, because if it were coplanar, we would have it on the plane. Okay, about 2 of that having it. So it is not option C. Then option D says trigonal core. That's your trigonal pyramid. So the correct answer is option D, trigonal. I hope you enjoyed this content. If yes, please don't forget to click on the like button, hit the subscribe button, and finally tap on the notification bell to keep you informed once we upload our next video. Question 131. Let's move on to question 131. The percentage of carbon 4 oxide in air is. Percentage of carbon 4 oxide in air is. This one, you just have to be familiar with the different composition of air. Don't forget that air is a mixture of gases. Okay, and the gases that make up air, we have nitrogen that has the highest percentage. We have oxygen, okay, that supports combustion. We have carbon 4 oxide. Okay, we have water vapor. We have argon, okay, like the noble gases. We have impurities and so on and so forth. Okay, so but the question says the percentage of carbon 4 oxide in air is what? We know that nitrogen contains about 78%, okay, composition of air. So, but we are not asked of nitrogen. Oxygen contains about 21% of air. We are not asked of oxygen. Carbon 4 oxide contains about 0.03%. That's the percentage, 0.03% of the composition of the entire mixture of air. And then we have argon containing about 1%, okay, of that. So the correct answer here, we have option A says 0.01. That is not it. Option B says 0.02. Option C says 0.05. Option D says 0.03. The percentage of carbon 4 oxide in air is 0.03. So the correct answer is option D. Question 132. An example of a physical change is, don't forget that a physical change is a change that occur, okay, when the substance, of course, reactants, okay, usually are reversible. Whatever product that is formed can be reversed to form the initial reactant back, okay. That is a physical change that has taken place. For instance, if you melt or you put your ice block or your water in the freezer, it freezes and turns to ice. You can bring that ice back again to turn to ordinary liquid. So that is a physical change because no new substance is formed. So we want to look at this example. Which one fits into that definition? Option A says exposing sodium metal to air. You know that sodium usually is in group 1, okay, and then group 1 elements are referred to as alkali metals. So their reactivity with moisture and air is very reactive. In fact, sodium is very reactive. It's highly reactive when exposed to air. It tarnishes so fast. That's why you will discover that sodium metal is not just exposed, not just kept. It's usually kept under a mineral oil or what we call kerosene, okay, just to ensure that it does not react easily. It's not exposed to air to cause. So because if it's exposed to air, it tarnishes, and then that substance that is formed becomes a new substance, because Na plus O2 is going to give us Na2O. Okay, so we are going to have a new substance that will be formed. So that eventually becomes a chemical change, not a physical change. So option A is eliminated. Option B says boiling of water. Yeah, if you boil your water, you apply heat to it. Once it boils, you have the vapor, okay, vapor that can be collected, okay, and then cooled again. As it vaporizes, it cools down and then it gets back to water, just like the method of distillation. Okay, you apply it, you cool it, and then you get your water back. So that means since we can get our water back, no new substance is formed. It is reversible. So this is a physical change. Let's pick option C. Dissolving calcium metal in water. Of course, it's not going to dissolve. Calcium metal will not dissolve in water. The only thing that will happen is that it's going to form a cloudy solution. Okay, it's just be there. A white cloudy solution will be there, but it is not going to dissolve in it. So, and then when you have it, you can have calcium then, which eventually leads to a chemical reaction that will lead to this. So we can't get our initial reactant back. So this, of course, a new substance is formed. So this also is eliminated because this is a chemical change. Option D says burning of kerosene. If you burn your kerosene, what happens? It goes off. It is fuel. Okay, so once fuel is burnt, you can't gather it back to get what you want. It is gone off. So this is also a chemical change. So this is eliminated out. So the correct answer here is option B, boiling of water. Question number 133. Boyle's law can be expressed mathematically as what? You need to know what the Boyle's law states. So if you know it, you can easily get what the answer is, because it's looking confusing. If you don't know it very well, you can choose, and take anyone for the other one. We have dealt with this question under our gas law in our chemistry video lesson. So you can also subscribe so that you can have this. You can see how we dealt so much about the gas law, the Boyle's law, Charles law, ideal gas law, Avogadro's law, Graham's law of diffusion, and so on and so forth. So many of them, and calculations were given on that. So Boyle's law, what does it state? Let's look at the board. Let's look at the board. Volume of a given mass of gas, okay, is inversely proportional. That's inversely, okay, proportional to pressure. It's looking at the relationship between volume and pressure, okay. Don't forget, at constant temperature. Okay, so Boyle's law states that the volume of a given mass of gas is inversely proportional to the pressure, provided that temperature remains constant. Temperature, that's the condition. Volume must be inversely proportional to the pressure, provided that temperature remains constant. So what it simply means is that what? As the volume increases from V1 to V2, pressure will decrease from P1 to P2, and vice versa. If pressure is increasing from P1 to P2, volume will decrease from V1 to V2. So they are inversely proportional. As one increases, the other one decreases. That's what we mean by inversely proportional. That's what Boyle's law is actually all about. So we have stated it said that volume of a given mass of gas is inversely. That's why we have 1 over P. Inversely proportional to P. So we can express this to be V. Remove the proportionality sign, it becomes equal to K, comes in. Once we remove the proportionality sign, then we have times what? 1 over P. Okay? So that will be V is, of course, K times 1 is equal to K all over P. Okay? Of course, you can make this over 1 and then you cross multiply. When we cross multiply, we have P times V. We have PV equal to 1 times K. We have K. So this is what Boyle's law states. And then that's why we have the formula to be P1 V1 equal to P2 V2. Okay, so this is what Boyle's law actually states. Looking at the relationship between pressure and volume, and then at a constant temperature. PV equals to K. Let's move on to the screen. PV equals to K. Okay, option A says PV equals to K. I think that is just it. Just it. Option B says PV equals to RT. No. This is looking at the ideal gas law, okay, where we have PV equals to nRT, okay, so this is not it. Option C states V equals to KT. V will be equals to KT, looking at the relationship between volume and temperature, and that is what the Charles law actually talks about. Looking at saying that the volume of a given mass of gas is directly proportional to the temperature, provided that pressure remains constant. That's Charles law, okay, but we are talking about what? Boyle's law. So this is not it, eliminated. And then option D is V over T equals to K. Option C and D are the same thing, because by the time you make this over 1, then you cross multiply, you have V will be equals to KT, which is also this, which is your Charles law. So this also is not correct. So the correct answer is option A, PV equal to K. Now let's move on to question 134. What is the vapor density of 560 centimeter cube of a gas that weighs 0.4 gram at STP, standard temperature and pressure? What is vapor density? Now, we know that there's a relationship between vapor density and molecular mass, okay? Molecular mass is 2 times vapor density. So, to get the vapor density, we need to first get the value for our molecular mass of that particular gas, because we're not given. So, once we get the molecular mass of that gas, then we can work our vapor density in to get our vapor density. So, let's look at what we're given. Let's move to the board. What is the vapor density? So, the question says, what is the vapor density? Usually, let's write the given parameters. Vapor density, question mark, that's the question, of 560 cm cube of a gas. 560 cm cube, that is volume. 560 cm cube of a gas, okay? That weighs 0.4 gram at STP. So, we're given the mass to be 0.4 gram at STP. So that's all we're given. So now, and we're given the molar volume of gas at STP, okay? Molar volume of gas at STP. So I will just use MV, molar volume of gas at STP, to be 22.4 dm cube, okay? Now you discover that we have volume given in centimeter cube, and then we have molar volume given in dm cube. So we must ensure that both of them are actually in the same unit, So if we convert this 122.4 to cm cube, that will be multiplied by 1000. That's going to give us 22400,123. Yes, 22400 cm cube now. So it's either it is 22.4 dm cube or 22400 cm cube. So don't forget, our aim is to get what? Molecular mass. Okay, once we get the molecular mass, then we'll be able to do what? We'll be able to get our vapor density. So there are 2 things we need to get here. So first of all, we have mass, because from what we're given is what we are going to use to find what we don't know. Okay, use the known to get the unknown. So we're given volume, we're given mass, we're given molar volume. So, but we know that volume and molar volume has a relationship, which is number of moles. In gases, number of moles, okay, because we are talking about gas, number of moles is actually equal to volume over molar volume. Of course, usually molar volume is a constant, okay, that is given, which is 22.4 dm cube or 22,400 cm cube. So, which means that N is actually equal to V over MV, okay? So, that will be equal to, the volume was given to be 560 cm cube over molar volume was also 22,400. So, by the time you divide this together, use your calculator, we have 0.025 mole. That is number of moles. Now that we have a number of moles to be equal to 0.025, and then let's look at the parameters we're given again. We have mass here. So there's a relationship between, done with this and this. So with the relationship between mass and number of moles, yes. So that will help us to get our molar mass, molecular mass, okay? So that will be, don't forget that also, number of moles in solids. Number of moles in solids can also be, number of moles can be equal to mass, okay, over molar mass, which is also our molecular mass, okay? Mass over molar mass, which is N, is equal to M over capital letter M, okay? So which means that we want to get this now, our molecular mass now, which is our molar mass, will be equal to, if you over 1 cross multiply, will be, okay, we have N, M here, then M. So if you divide both sides by this, so this will be divided by, M will be divided by N, okay? M will be divided by N. So which is equal to, we have mass was given to be 0.4. So we have 0.4 gram divided by The number of moles, 0.025 moles. Okay, so by the time we divide 0.4 divided by 0.025, we'll be having 16. So 16 will be our value for molecular mass. So our molecular mass is, for that gas, is actually 16. Now that we have gotten the molecular mass to be 16, I think we can get our vapor density. Now remember that vapor density, okay, just go this. Recall that molecular mass, which is our molar mass, is equal to 2 times vapor density. So molecular mass was obtained to be 16. So we say 16 is equal to 2 times vapor density. So we divide both sides by 2. Vapor density will be equal to 8.0. 8.0 will be our vapor density. So let's look at the screen and see what we have from the option. Option A says 6.0. Option B says 8.0. Option D says 16.0. Option D says 32.0. So the correct answer is 8.0. Option B is the correct answer. Do you have any question bothering you at all? Please feel free to ask. All you need to do is to click on the link in the description below that takes you to the Myschool website. There, you'll be able to ask your question and solutions will be provided within the shortest period of time. Now, let's move on to question 135. When the subsidiary quantum numbers L equals 1, the shape of the orbital is what? Don't forget that we have about 4 quantum numbers, okay? We have the principal, we have the subsidiary, or what we call the azimuthal, okay? We have the magnetic, and then we have the spin, okay? But in this case now, the question says, what is the subsidiary quantum number, okay, when L equals 1? Don't forget that the ranges of values of azimuthal of subsidiary quantum number is actually ranging from 0 to 0, 1, 2, and so on. So let's look at the board, okay? Azimuthal, when it is subsidiary has the range of values moving from when L is 0, when L is 1, when it's 2, and so on, okay? Now, when L is equal to 0, usually it falls in the subshell orbital of S, okay? That's why we call it S orbital. Okay, usually S orbital subshell. When L is equal to 1, the subshell of P is what we have, P orbital, SP. Okay, when L is equal to 2, subshell will be D. Okay, and so on and so forth. So let's not move further. Okay, now, but the question says that when the subsidiary quantum number equals 1, so the shape of the orbital, of course, when L is equals 1, that is what? The P orbital. So it falls in with the P subshell orbital, okay? The P subshell. And don't forget that the P, usually we have 3 orbitals, suborbitals. Under that, we have Px, we have Py, we have Pz, okay? We have this, okay? The X, then we have another one here. We have the Y, we have the X, we have the Z, okay? The same thing happens here. So usually we have, for the P, we can have it this way. This one moves this way. So we have this one this way, okay? And then for this, we have this moving this way. So for Px, we have Px, Py, and Pz. Usually you are going to have a dumbbell kind of shape, okay, for this P orbital because of the 3 subshell that we have under. Don't forget, when L is equal to 1, we have the P orbital, so, and which has about 3 of them, okay, which gives a bell shape kind of, okay, like a dumbbell shape. So for the Px, Py, and Pz, let's look at what we have on the screen. Option A says spherical. That's not spherical. We have the dumbbell, we have flat, and then we have round. So the correct answer here, when the subsidiary quantum numbers L equals 1, the shape of the orbital is the P orbital, which has a dumbbell shape. So the correct answer is option B. Do you have any better explanation or better steps to solve these questions that we have gone through? Please feel free to share. All you need to do is to go to the comment section, indicate the question number and the answer you wish to share. Please feel free to share. Question number 136. Esterification reaction is analogous to what? That means what other name fits into this esterification? Okay, don't forget that esterification reaction is a reaction that involves alkanol reacting with alkanoic acid to form alkanoate and water, what we call ester. That's why we have the esterification. Let's look at the board to see. Let's write it. So we have alkanol plus reacts with alkanoic acid, okay, to give alkanoate, okay, plus what? Plus water. Okay, so we can have an example. Alkanol, let's have ethanol, for instance, C2H5OH plus alkanoic acid, we have CH3COOH, and then this gives us we have CH3COO. Of course, the hydrogen will be off with this OH here to form water. Okay, then we have C2H5 left here plus the water that was formed here. So this is our ethanol reacting with ethanoic acid, and then we have ethyl. This is C2. Okay, so that comes first. We call this ethyl ethanoate because we have two carbon here. Okay, carbon atom, ethyl ethanoate, and then we have our water here. So this is a typical example. Of course, this can be reversible. I'll just do this reversible. This is reversible in that the forward reaction is esterification, okay, while the backward reaction is hydrolysis. So in other words, if you react alkanoate with water, you will form alkanol and alkanoic acid. Okay, that is hydrolysis. So the question says that esterification reaction is analogous to oxidation reaction. It cannot be oxidation reaction because there is no addition of oxygen to this. What we just have here is what we have here. So oxidation is not what is taking place here. Okay, so it cannot be oxidation reaction. Option B says neutralization reaction. This cannot be neutralization because neutralization reaction actually involves reaction between an acid and a base to form salt and water. Okay, acid, we have an acid here, then this is not a base. Okay, so base, and then we have this is ethyl ethanoate. We have, this is not a salt and water. Okay, and then we have option C says condensation reaction. Okay, condensation reaction, yes, it can be condensation reaction because we have smaller molecules combining together to form a larger one. Okay, condensed together, and during a condensation reaction, a molecule of water is usually lost. Okay, so we have ethanol, we have ethanoic acid to form all of them together. What was lost was just what? The water that was formed at this point. So this is a form of condensation reaction. And option D says hydrolysis reaction. Hydrolysis reaction, like I said earlier on, is the reversible reaction of what? Esterification. Okay, so the backward reaction is what gives us hydrolysis. So it is not esterification. So option B, if you look at this, yes, there's OH here because there's an option. The option B says neutralization reaction. Okay, this is an acid. You can be tempted to say, since we have OH here, so this is a base. No, of course, this is ethanol. Ethanol is not a base, so you cannot say it's a neutralization reaction. So based on that, let's look at the screen. Option A says oxidation reaction. No, it is not oxidation reaction. Neutralization reaction. No, base is not reacting with acid. Condensation reaction, yes, it can be because we have a larger molecule of ethyl ethanoate or alkanoate is actually formed, okay, and losing a molecule of water. Option D says hydrolysis. Hydrolysis reaction is the reverse reaction of esterification, so they are not analogous to each other. So the correct answer here is option C, condensation reaction. Question 137. The IUPAC nomenclature of the compound CH3CH2C, CH3, C double bond here, CH3 2. For the compound is what? We have 2,3-dimethyl pentane and so on and so forth. So let's draw the compound first. Let's go to the board and let's draw the compound. We have, okay, I'll just write it out. We have CH3, CH2, we have C in brackets. This is what we call the condensed form. Okay, condensed form of the compound C. Then we have CH3 here. Then we have 2 for the compound. Okay, so first we need to draw this. If you draw it out perfectly well, then I think naming it should be easier. Okay, so to start with, we take CH3. So we have C here, 3H, 1, 2, 3. That we have with bonded to carbon, then H2. That means we have 1, 2. Then the next one we have carbon here. So that means that's a bond there, carbon here. Then this carbon has CH3 attached to it, as CH3 attached to it, as CH3. So we have CH3, okay. Then we have it this way. We have double bond here, 1, 2, 1. If you count the bond for this carbon, we have 1, 2, 3, 4. So it's completed. Okay, so this double bond is what it is. Then we have carbon here. Then this carbon has CH3, 2 attached to it. So we have CH3 here. This is one CH3. Then the second one is attached to this end. Okay, so that's what we have. So this is the compound we have. This is the condensed form. We have been able to expand it to be in this form. So now to start with, let's look at the naming. Let's look at the name. The first thing we do, like we said earlier on, is what? To look at the longest chain, okay, to get the parent name of the carbon chain. So if we count from here, we have 1, 2, 3, 4. Okay, we can have 1, 2, 3, 4, 5. Okay, we can also have 1, 2, 3, 4, 5. Okay, I think 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. So the longest carbon chain is actually 5. So the parent name should be 5. So the name with the parent name carbon atom 5 should be a pent. Okay, so we have pent. So we'll form that first. We have pent because it has 5 carbon atoms. But don't forget, we have a carbon-carbon double chain here. Okay, carbon-carbon double chain here. So we look at it because it is carbon-carbon double chain. That means it is what? Alkene. Okay, so it's going to have this. But on what carbon atom do we have this double chain, this double bond that we have here? We have carbon 1. If we name it from here, carbon 2, carbon 3, carbon 4, carbon 5. Okay, so which means that the double bond between the carbon-carbon is actually on carbon 2. Okay, so if you go from this route and if you come from this route, you have carbon 1, 2, 3. Okay, then 4, 5. So that means it's on carbon 3 here. So carbon 3 tends to be what? To be longer. And the rule says what? We go with what? The shorter route. This one is carbon 1, carbon 2. So it's on carbon 2. So that means this is going to be pent 2 in because it's an alkene. Okay, pent 2 in. It is double bond. So double bond should be in. If it were a triple bond, it would have been YNE from the alkyne. Okay, it would have been that. So the double bond, the number of chain is 1, 2, 3, 4, 5. So that's why we have the pent. But we have a double bond carbon-carbon on carbon 2 from this. Well, if you count from here, so that is we have 2 in. So it shows the positioning of the double bond is on carbon 2. So we are done with the parent name. So the next thing to do now is to look for the substituent that we have, the other functional groups that we have on this compound. We have, this is one of it, this is CH3 on this point. Okay, we have another CH3 which is your methyl group on another one. So we have it here. I think those are the 2 functional groups we have. Okay, so already we have named them accordingly to the carbon. So if you count from here, we have carbon 1, carbon 2. So we have 1 methyl on carbon 2, then we have another methyl group on carbon 3. Okay, carbon 2 and carbon 3, counting from this one, carbon 2 and carbon 3. So which means that we start with this first. Both of them are methyl, they are the same. So that is di. We use the prefix di to show that what there are 2 because they are the same. So we take the first one first. The first methyl group is on carbon 2. So we will say 2. Okay, we would have written 2 methyl, then 3 methyl. But since both of them are the same thing, so we just say 2, 3 dash. How many methyl groups do we have here? We have 2 of them. So we have di. Okay, methyl pent-2-ene. Okay, so that should form the name. So we have the parent name that is pent-2-ene. Then we have the positioning of the methyl group. We have 2 methyl group of position 2, carbon 2 and carbon 3, and that's what we just have here. So in other words, we are saying that the IUPAC nomenclature for this compound is 2,3-dimethyl pent-2-ene. Okay, dimethyl pent-2-ene. So that is the IUPAC nomenclature. Let's look at the screen and see the options we have. Option A says 2,3-dimethyl pentene. Okay, that is wrong because this is pentene. They didn't tell us on what position we have the double bond. Okay, so option A is wrong. We eliminate that. Option B says 2,3-dimethyl pent-2-ene. Yes, 2,3-dimethyl pent-2-ene. More likely what we have there from what we had, 2,3-dimethyl pent-2-ene. So this is correct, showing that the double bond is on carbon 2. Yes. Option C says 3,4-dimethyl pent-3-ene. Okay, 3,4-dimethyl pent-3-ene. This one is looking at counting from, let's look at the screen, counting from here. If you count the number of carbon atoms from here, carbon 1, 2, 3, 4, 5, okay, then it will be carbon 1, 2, 3. So this would have been 3, okay, 4 dimethyl, and then this double bond would have been on carbon 3. So it would have been pent-3-ene. That's what would have given us that option C, so which is not correct. You must count from the side that has the shorter. Let's move on to this. So we see option C is actually not correct. Option D says 3,4-dimethyl pentene. So this also is not correct. So the correct name for this is 2,3-dimethyl pent-2-ene. So the correct answer is option B. Question number 138. Now, the reaction above illustrates this. We have ethanol here to give us ethene. Okay, we have in the presence of H2SO4, conc H2SO4 at a temperature of 170 degrees Celsius. Let's look at the board and see what happens. This is ethanol. Okay, in the presence of reacting with conc H2SO4 at a temperature of 170 degrees to form ethene, and then you have H2O living there. Let's look at the mechanism of the reaction. We have CH2HO here, okay, reacting with H2SO4. This will give us, of course, at a temperature of 170 degrees Celsius. We have C2H5 first. Now, this OH here, okay, we react with 1 hydrogen from here. No, we have 2 hydrogen here. So to form water here, 1 hydrogen with this H2O will form water here. So 1 molecule of water has been removed from there, and then we'll be having SO4 with 1 hydrogen that is left here. Okay. So we have that C2H5. We have that. This is what is formed first. Then this now C2H5SO4H now reacts again. We subject it with that. What happens now gives us what we have at C2H4. Okay, we can have it H2O, H2SO4, or we have it here C2H4. Then we have 1 hydrogen here reacts with this to form H2SO4. Okay. So in other words, molecule of water was removed, okay, was dehydrated from this. Ethanol became dehydrated to form ethylene, okay, what we call ethylene or what we call ethene. So this reaction now, I just wanted to show us what happens for us to have this C2H4, which is ethene, okay. So water molecule was removed from this to form this. So when there is removal of water, okay, molecule from a compound, we call that dehydration. Let's move on to the screen. Option A says oxidation. Oxidation is not because we are not adding oxygen there. Okay, we have esterification. There's no ethanol reacting with alkanoic acid, even though this is an acid. Okay, ethanol reacts with this acid, but this is a conc H2SO4. It is not an alkanoic. Okay, it's not an alkanoic acid, so it is not esterification. Option D, C says dehydration, because yes, water molecule was removed from the ethanol to form ethene or ethylene. So we say option C is correct. Option D say polymerization. We don't have two or more monomers. Okay, smaller molecules combining to form a larger one. So option D is also not correct. So the correct answer here is option C, dehydration. I believe you enjoyed this content because I really did solving those questions. If yes, please don't forget to click on the like button, hit the subscribe button, and finally tap on the notification bell to keep you informed once we upload our next video.